Yeah, yeah. Hi, both of you. So I think let's to join Sadar. Okay, fine. If you have any query in any particular questions or any topics, so you can ask in the week 7 or maybe earlier weeks. So do you have any query, Jiptesh, Madhav, Mayank, Chandresh?
Yes, sir. There was this discourse post in which Bhaskar sir said he will explain how to get how to visualize the tree from pre-order and post-order BST tree.
Okay. So BSc pre. Okay, okay, fine. So we have to take first to pre-order and post-order. Correct. Okay. So do you have any example where the pre-order and post-order is given for any tree?
Uh, I don't have at the
Okay,
moment.
no problem. So we will calculate first. So okay, I'm drawing a tree here. Like this. Okay. So this is a tree we have, and first we will create a pre-order and post-order for this. So what will be the pre-order? and what will be the post order.
Root.
Okay, so pre-order we can start from the root. In the pre-order we always first read the node value, and then we traverse the left node, and then we will traverse the right node. This is the pre-order operation. So here we are starting from the root, so definitely A will be print first, and then we will move to the left child. Then when we are moving to the left child, then we will apply the pre-order algorithm on the B node. So same things, B will come, and then from B node we will move to the D node. So now D will come, and now there is no left child and there is no right child. So we will come back, and after when we are returning to B, so right traversal is remaining for that. So we will move to the right child, and now in that when we are at E, so first operation is our read the value of node. So this is a E, and then move to the left child. So this is a E. Now move back, and after that we will move to the right child, and there is only node G. Then we will move completely from A. So all node have already traversed. Now we will move to the E, then B, then A. Now the right child is available for A. This is only C. Okay, so this is a pre-order, correct?
Yes, sir.
Okay. Now we will create a post order. So for post order, our algorithm is first we will traverse the left child, then we will traverse the right child, then we will read the value of node. So when we apply this algorithm, so first step is traverse the left child. So we will traverse the left child at node B. Then the first step is traverse the left child. So left child is also available D. Now there is no left available. Then we will check for the right. So right is also not available. Then we will read the value. So now first value will be printed as D, and then we will come back on the B. Now we will move to the right step. Okay, so first step is left, then right, and then print. Okay, so I'm written as here. So at the B, second step is right. We will move to the E. Now the first step of this algorithm is left. Then we will move to the left child. Now there is no left, there is no right. Then we will read the value. So F value will be printed. Now we will move back to the E. Then we will traverse the right step, second step. Okay, so there is no left, right. Then we will traverse the G. So same when so we will return back. And during the return back, now the left we have already visited, right we have already visited. Now we will read the value E. Same things for here. Left we have already visited, right part we have already completely visited. Now we will traverse the value B. Now for A, so left part have completed for A. Now we will traverse the right part, the second step, right part. So we'll move to the right part. Now C, so there is no left, right. So we will traverse the C, and then back at the back time of we will read the value A. So this is the order of this is the traversing order, pre-order and post order for this tree. Now our next purpose is how we can create a tree using these order.
Yes, sir.
Okay, so we know that in the pre-order traversal, the first node is always a root node. Same for the post order. We know that the last traverse node is a root node. So that means these are the root node. So we can easily create a root node here.
Yes, sir.
Okay. After that, how we can decide the what is the left child and what is the right child. So for left and right child, so we will calculate using this. For example, we will check n1 and n2, two value for every node. What is the n1 is? So we will check that what is the okay. What is the successor of current node in pre-order. Okay, and this is a predecessor of current node in post order. Okay, so we will read this value n1 n2 for each node when we are checking that what is the left child and what is the right child for that. So we will check this information in both order, and after that, if n1 equal to n2, that means both value are same, then we can make n1 either of left child or right child of current node. Okay, left or right, we can add in any direction if n1 equal to n2. Else we will make n1 left child and n2 right child. Okay, so 1 second, I think yes. Now for a, now check that what is the n1 value or n2 value for a. So you can check that n1 for a, so I am writing here n1 for a is, so we will check that successor of current node in pre-order. So what is the successor of a is b, correct? We will note down this b, and for n2 we will check that what is the predecessor of current node in post order. So predecessor of a in post order traversal. Okay, we will still look at in this post order traversal. So what is the n2 value is c. Now we will check if n1 and n2 are same. No. So we will perform these steps. We will make n1 as a left child and n2 as a right child. Okay, we will also mark that this node have already become a part in our tree. So b is also created. Now c is also created. Okay, now we will not repeat this again in our tree. So now first step is complete. Now we will check that what is the so we don't know what is the child of c, what is the child of b. So we will check for both. So we will check for example for b. So what is the n1 value for b and what is the n2 value for b? So n1 value is for b is, so we will check that the successor of current node in pre-order. Okay, so this is d. And what is the n2 value? This is the predecessor of current node in post order. So this is a e. So this is d and this is e. So both are different. We will connect in the same way. So d and e. Now we will mark that those have already become our nodes. So d and e. Okay. Now we will check for c. Okay, what is the value for c? So n1 and n2. So for n1, we will for c we will check what is the successor of current node. So there is no successor here. You can see c is the last node. So that means there is no successor. Same things we will check for the here. What is the predecessor of current node in post order? But here the predecessor is b, but b is already included in our tree. So that means there is no predecessor available for c. So though there is no that means there is no child available for c in this case. Now we will check for d, n1 and n2. So same for the d. So we will check what is the successor. So what is the successor of d is e, but this e have already included in our tree. So that means there is no successor. So no information. Now we will check for n2 what is the predecessor of this D? So there is no predecessor. This is the last one. Okay, that means there is no child for that. Now we will check for the E. N1, N2. Now you can see that what is the successor of E is G. And what is the predecessor of E in post order? So this is the E. And what is the so this is a G. Okay. No, G no.
F should be successor shouldn't be F.
No.
Hello, sir.
Yeah.
Sir, it is for converting from pre-order to post-order.
No.
Are you-
Actually, we are creating a tree using pre-order and post-order combination.
Okay. I have
Okay.
doubt. After this, I will ask. Okay.
Okay, sure. So for E, we will check that what is the. I think something is. What is this? This is F.
This is
okay.
E, and the next one is F.
Yes,
Okay.
that is
Oh, because of that I missed this. Okay. So what is the successor of E is F. So this is also. So this is a F, and what is the predecessor of E is G. Okay, so both are different. So we will add this as a left child, and this is a right child, and we will mark that in our book. So now all nodes have marked in our tree. So now you can see that we have created a tree. So in some case, there is a chance our tree maybe not create exact the same. So for example, in this case, so N1 and N2, if both are equal. Okay, so if I include, for example, if I include one more child here, so in that case, we cannot identify that this node is a left child and right child when we are creating a tree. So we can add this single child in any one direction. So either in left, either in right. So this is the combination. So this is the one differentiation. We cannot create exact trees. But if we are adding a single child in either a left or right, and that is the only single child, there is no other child available after that. So pre-order and post-order, if you will create for the trees, that will remain the same. Okay. So this is the process of creating a tree using the pre-order and post-order. Okay, so what was the question someone is asking?
Yes, sir. So suppose we have given a pre-order query, right? And we have to convert it from pre-order to post-order. So how can we do that?
So for binary search tree, you can create.
Yes. Suppose we have given a pre-order binary search, right?
So you can simply create a tree, and then after you can traverse as a post order.
So can suppose
okay,
there is there is a query, right?
So I'm just first creating a one binary search tree. Okay. So for example, 10.
No, sir. From not that side. I mean, we have given a query, right? It is not given any tree or like that.
I got at your point. Actually, first we have to need one pre-order now. So
yes,
if you have a pre-order, you can please send me in chat box.
Yes.
Do you have any sequence of pre-order?
Okay, yes, sir. I am sending you.
After that, I can. Otherwise, I have to create one pre-order first for any binary search. Then I can explain.
Yes, sir. I am sending you.
Okay.
15, 10, 12.
Oh, one second. So 15, 1, 10.
Sorry, 1, 15, 10. It is not 1, sir. 15, 10.
Okay.
12. 11, 20, 18.
11, 20, 18.
16, 19.
16, 19.
Yes.
Okay, correct?
Yes, sir.
So this is a pre-order, no?
this is given pre-order. Yes.
Okay, and this is pre-order for binary search.
Yes, this is a binary search for binary search tree, and we have to find the post order.
Okay, so you can simply create a binary search tree using this. So you know that in the pre-order traversal, always first node is a root node.
Root node, yes.
Okay, so you can just simply add this as a root node. After that, simply insert the all element one by one in a using the simple binary search insertion rule. So 10, we will insert the 10. So 10 is less than 15. So this will include here.
Okay.
Okay.
So,
now 12. So 12 is less than 15, greater than 10.
Right. It is in right.
And 11 less than 15, greater than 10, and less than 12. So okay, we will insert here. Now 20. So 20 is greater than 15. Simply insert here. Now 18. So greater than 15 and less than 20. So it will come here. 16 greater than 15, less than 20, less than 18. This is will come here. And 19, 15 greater than 15, less than 20, and greater than 18. Okay. So this is a tree, binary search tree for this pre-order. After that, we can traverse using a post-order traversal.
Yes, sir. Now I can do.
Okay, simply apply the post-order traversal norm and you can find.
Okay, and if we given post order and then we have to convert it pre-order, then
same process.
We have to first. Sir,
but yes, you have to scan from the last.
But in post order, we have the first element is left, right, and the parent node, right?
No. In post order traversal, for example, this is a post order traversal. So last node is represented as a root. You remember these things. In the pre-order traversal, always first node is represented the root in tree, and in post-order traversal, last element is represented as the root.
And in order?
In order, root can be come in any place in between. So we cannot find out the root in order traversal.
Suppose we have given an in order and we have to.
Yeah, so we cannot create.
We cannot create, no?
Yes, we cannot create for only in order.
What operations can we do in order transversal?
What operation means?
Suppose means we have given an in order and we cannot convert it.
Yeah, we cannot using only in order traversal. We cannot create it by in the search tree.
Suppose we have to create a binary search for in order. So we can create or not?
No, I'm not getting.
Sir, suppose we have given an in order transversal and we have to create a tree like a structure. Can we do that or not?
So same thing I'm telling you now. So we cannot create, we cannot recreate actually. I don't know where from you get the in order traversal. So we cannot create the same tree using the in order traversal only. If we have a combination of so in for binary search tree, we can create a binary search tree, recreate a binary search tree using only pre-order traversal or only post-order traversal, but cannot be created using only in order traversal.
Okay.
Because in order traversal, we cannot identify the root.
Okay.
But for the normal binary tree, I'm not talking about now binary search tree, but for normal binary tree, if we have a combination, for example, we cannot create a binary normal binary tree. We cannot recreate a normal binary tree only by in order or only post order or only pre-order. We need any combination of two for recreate a binary tree. So in the previous example, for example, this is a tree. Okay. If we have a in order of this tree, we cannot recreate this.
Okay.
If we have only pre-order for this, we cannot recreate this. And if we have only post-order for this, we cannot recreate. But if we have any combination of two, in order or post-order, in order and pre-order and post-order, so we can create.
So is it because numbers are not there, it's alphabets are there, that's why?
No, in normal binary tree, we cannot identify who is the left or who is the right. Because in the binary search tree, there is a property. Left is the smaller and right is the greater. because of that we are creating only by single.
Okay,
But
sir. Okay.
but for normal binary tree we cannot identify who is the left or who's the right. Okay, so for normal binary tree we need any two combination to recreate. Okay. This is an Discord post. This is topic. Oh, Jivitesh, we have already discussed, or this is the something different?
I was giving the other person the reference to this post. I was giving the reference to this post to the person who was asking about this.
Oh, okay, okay. Okay, any other query in any topic or questions? Regarding AVL tree, the first topic of the week 7 is the AVL tree, or we can also take a question for the BST because AVL tree is create the binary search, balanced binary search.
Sir, can you explain job scheduling? I mean, I
Okay,
know job
scheduling.
how it work. I know, but in 7.3, I think the lecture 7.3.
Interval scheduling.
Yes, interval scheduling.
Okay, okay.
Yes, that part I
Okay.
understood, but not the concept is not so much clear.
Okay.
Can you tell me briefly?
So is there any query in AVL tree or binary search query? Binary search tree.
AVL tree. In AVL tree, you can. It is better if you explain the insertion that is asked in the field assignment.
Insertion operations. Okay.
Yes, with the code. Yeah,
so you want to discuss the code or concept?
Code only. Concept, I think we already discussed enough.
So where is code? Okay, so there is one code is given. So this is a code for insert operation. Okay. So insert operation, what we are doing actually when we are inserting here, we are checking that if tree is empty or not. First thing, okay. Self dot is empty. If it is empty, we will directly add the first node, add as a first node, as a root node. We can see that. Okay, this is the first step. If self dot value equal to v, return. Okay. So this is the similarity of value. For example, we are repeating any insertion. We have already some value v, and we are inserting again. So in that case, we are not inserting this. Okay, so this is the second condition when we are inserting a value in our tree. Okay, so this is a simple binary search insertion concept, but after insertion we are performing a rebalancing things in the AVL tree. Okay, so rebalancing thing is the important things. Yeah, otherwise not. This is a normal binary search insertion. So we always start from the root. And then we compare the value. When we found the empty place to insertion, so we at that place we insert. So this is the process of binary search tree basically. So if the tree is empty, then we are directly making a node with the value v. If value have already in our tree, then in that case we are not doing anything. Otherwise, we will comparing our value. If v is less than of our current node value, self dot value, then we will move to the left side. Okay, so this is a self dot left dot insert. So this is a recursive call on the left child. Same operation we are applying on the left child. Initially we start from the root. So if root where our inserted value v is less than the root node value, so we will move to the left child side, and after moving on the left child, we will apply this insert algorithm on our left child. Okay, So same things we will repeat until we will found the empty place. Same thing, so that this is the next condition. If our value is greater than of our, to our current value, so we'll move to the right side and we will apply this same insert operation on our right side. So after insertion, so at any time we will insert our node at the correct place according to the binary search condition. But after binary search insertion, we will apply this rebalance things, because after insertion maybe our tree may become unbalanced, and so we will apply this rebalance thing. And in rebalance thing we will check, we will calculate all these things, height and all these things. So this is the rebalance algorithms. And there is one also a height update height. So here you have to understand the concept of how we will insert these things. So for example, in AVL tree, so for insertion you have to clear all the rotations type things, how we are perform the rotations. If you have cleared these rotation things, so we can directly apply this. So for example, initially we have a node 1. Okay, so in that case this is a simple one node. So the balance factor, so main one thing is the balance factor, or sometimes we call the different things. So for example, we have this sequence 1 2 3 4 5. Okay, so we will insert first, there is no balance factor, so every time we will calculate the balance factor. If the balance factor is greater than 2 or less than greater than 1, sorry, greater than 1 or less than -1. Okay, so we will apply the rotations. So after insert every time, so we will insert our element according to the binary search concept. So for 2 we will check from the root and 2 will come here. Okay, in that case after every insertion we will calculate the height of each node. We will update the height of each node, and we will calculate the balance factor for it. So for example, this after insertion 2 we will update the height. So height for example, we are taking the height of single node as a 1, so we will update the height like 1, and height for this is 2. Okay, so there is no left child, there is no right child. So for in binary search tree, basically we are adding a dummy node for each node that contains a height 0. So every last node, I think we generally insert a dummy node. Okay, if you see the complete class, so yeah, this one. So when our tree is empty, we are adding one self dot value equal to v, and we are inserting a one dummy node. So self dot left equal to AVL tree, and self dot right equal to AVL tree. Inside this AVL tree, one node is actually creating as a dummy node. So when we are calling AVL tree, that means one node is created with value as a none. So you can see if we are not passing any value, so none value will be created for that node, and height we are assigning as a 0. Okay, so self dot left equal to none, self dot right equal to none, and self dot height equal to 0. So every time when we are adding new nodes, so two dummy nodes are created for that last node, and that contains a height 0. So using this, we will update the height of our tree. After that, we will calculate the balance factor. Okay, so we will calculate the balance factor from the last node inserted. So in the last we have inserted 2, and we will update. We will calculate this balance factor till 2 from the last inserted node to the parent root node. Okay, so we will calculate the balance factor for this 2 nodes. So this is a left height minus right height. So what is the left height is this 0. This is a 0. 0 minus 0 is 0. Balance factor is 0. Then we will check for the parent also. So same for 2. So there is no child here. So that means there is one dummy node will be added. So the height is 0. Now the left height is 0 and the right height is 1. Okay, so left child height is 0 and right child height is 1. So 0 minus 1 is -1. That means there is no problem with the tree. So then we will not perform any rotations. So for the same things for the next insertion, so 1, 2, and 3. At this time, so this is the dummy node where we are not inserting any node. So that is dummy node. This is contains a 0 height. So at this time, 0 plus 0, so this is a 1 height, and now this is the max. What is the maximum height over this is 1 plus 1 is 2, and here this is a 1, 2 plus 1 is 3. Okay. So for height, generally we consider the longest path from root to leaf, current node to leaf. Okay. So this is 2. Now we will calculate the balance factor. So for 3, balance factor is 0 minus 0 is 0. Now balance factor for 2 is 0 minus 1. So this is -1. Now balance factor for this one node is 0 minus this 2. So this is 0 minus 2 is -2. So any stage we found this -2 or +2, this value. So you can see, so in the rebalance, actually in the rebalance part, yeah, this is the rebalance things. If self dot left height equal to none, then we are assigning, that means there is no child in the left. We will directly assign this none value. Okay. So if self dot left equal to none, so for any node, if there is no child at the left side, so we will assign this HL left height as a 0. Else, otherwise we will read the value of the left child. Okay. So for left height, if there is no node available, so we will assign a 0 height, and if there is a node available at the left, so we will read the height of that value. So here we are reading the left child height, and same for the right. Here we are reading the right child height. If it is not available, so we are assigning 0. Otherwise, we will read the value of height, right child. So after that, we are checking that if the HL minus HR is greater than 1. Okay. So HL minus HR. So here left height minus right height is greater than 1. So that means this condition is represented that our left side is the height, if our left side height is more than the right side height. Okay, in that case we apply the different type of rotation. So we call this clockwise rotation, we can simply say. Okay, same for if HL minus HR is less than -2, then we apply the anti-clockwise rotation. So this is the code for anti-clockwise rotation. So these things we apply. So here we found the HL minus HR is -2. Okay, so in that case we will apply the anti-clockwise rotations. So for rotations, so there is simply code. Here we will simply call the left rotate things. So after that we are also checking one more things. So actually there are 4 type of rotations. So there is one rotation, for example this type L rotation. For example, there is no child here, and all nodes are 2 nodes are connected on the left. So this is called the left rotation. So in that case we apply the clockwise rotation on this node. Okay, so after rotation our tree will become, for example, this is A, this is B, and this is C. So our tree or after rotation it become like a B, A, and C. So this is a first type of rotation we call as a LL rotation. Okay, second case is RR rotation. So in that case A, B, C. Okay, so in that case we got this -2 value, and we apply the anti-clockwise rotation, or we got this rotation after rotation, this type of information A, C. Okay, this is called RR rotation. So this is left F and this is R. So this is 2 types, and after that there are 2 more type also. So for example, we have A, we have B, and we have C also here, and then okay. So A, B, C, D. Like this type. Okay, so this type of rotation, so you can see here the left had 0, right had 0, so balance factor will become 0. Same for here, so left had 0, right had 1, so 0 minus 1 is minus 1. Here left height is 2 and right had 0, so 2 minus 1 is 2. And here also, so for A, so in that case, this is also 3 and minus 1, so this is also 2 and this is become 0. So at any time, so we always check the rotation from the bottom side, okay, because we are apply this insertion algorithm recursively. So at the time of return, we apply this rotation operation. So after insertion, for example, the last, so this E is the last insert element. So we will check the this balance factor value from the bottom side. So at 10 we will get this 2 value. So at place B we get this 2 value. We will apply the rotation on that node. So this is a condition of left right rotation. Okay, left and right. So this so we are getting this 2 value on B. So the child of B is coming on the left side and the last inserted node is coming on the right side. So this is called the left right rotation. So in that case, we apply two type of rotations. So first rotation we apply here on the D. This is a anti-clockwise rotations. So after this, our tree become like A, B, and E and D. Okay, then C. Then second rotation we apply on that B node, and this is a clockwise rotation. So after that, A, C, and this E will come here and B will come here and D. Okay, so after two rotation, this is called the LR rotation. So LR rotation. So after two rotation, we got this balance tree. So now balance factor is 0, 0, 0, 0, 1. So similarly from the RL rotations. So same if we make it in the different side. So there is one RL rotation. So these so for checking these two type of rotations. So for example, if we are getting this 2 or minus 2 value on any nodes, so then we will check that this is a RR or this is a RL or this is a LR. So this is a LL or this is LR. So because of that, after we are getting this positive value, so in that case we will check we are checking the height of the child value. So this is so. For example, this first condition is representing basically for if we are getting a left rotation. So we are applying only one rotation at that time, right rotation. So second condition, if this condition is not true, so we will check the second condition. This second condition is representing for a left right rotation, LR rotation. If this condition is true, so we will apply two rotation here. One on the left, so here we will perform the left rotation first on the left child, and then we will perform the right rotation on the that node which have the value 2. So these things here we are performing both type of rotation after checking this is a LL condition or this is a LR condition. Okay, so we will after applying the rotation on the child node, so there is no need to check the parent node after that. So definitely after apply these two rotations, so upper value, so we are getting this 2 value on the A node also. So that will also become it. So that will value also reduce after this rotation. So no need to check on the parent after this rotation. So this process actually we are performing recursively in our solution. So you can see after this insert operation. Okay, so this is a recursive call. We will move to the last node when we are inserting the B, and at the return time we are calling this rebalance things. Okay, so after rebalance things, we are also calculating the height for this current node. We are updating the height also. So this is the formula for height for each node is 1 plus max of left height and right height. So same things we are performing recursively. So at the after insertion, we will check these things after in the rebalance things. We will check the balance factor from the bottom side. if we are getting the variance factor 2 or minus 2 or more than, so we will apply this 4 type of rotations: LL rotation, LR rotation, and this is for RR rotation, and this is for RL rotation. Okay, so this is a process to add. Okay, any query?
Thank you, sir. for
Yeah, Kesav?
Hello, sir.
Yeah, Kesav.
Sir, I have a doubt in this binary trees. I want to say that a tree can have on the left side, it can have all the less. I mean, the value should be less than the root node. But if the value, if the root, if the root node has a left child which is less than its value, but that left child can have a right child which is greater than the value of the root node itself. So
No,
how
no.
can we say?
So in binary search tree, I think you are not clear in the concept of binary search tree. So you are saying that if, for example, this contains 20 value, okay, the left child
Yes.
value contain a 10 value, and the right
Yeah.
child of that value contain a 30 value.
Yeah.
This is not correct. Actually, according to the binary search tree condition, so all the
Yes.
value of in the left subtree, left child as well as the left subtree should be
Okay.
smaller than this node.
But when
And
we are in the child node, then how will we know that what was the value of the root node of that child?
so
I
because of
mean,
that,
when we are in,
at the time of insertion, we always compare from the root.
okay,
At the time of insertion, for example, if you have a 20 value in the initial tree and 10 is the these things, if you have a this binary search tree, so when you are
yes,
inserting 30, so you will not add this 30 directly here. You will always start from the root node is, and then you will compare this 30 from the root node, and according to the condition, it is greater or lesser, you will move. So 30, when at the time of insertion, we will compare this 30 from the root node. Then we will check 30 is smaller or greater than this root node value. So this is a greater than value. So we will move to this side.
okay,
Okay, we will never move to the
yes.
smaller side.
Then
So
we have to check the whole tree for that.
no, so at the
I
time of
mean,
insertions, you will always insert in that way.
no,
So
if
your
the tree has height, let's say the height of the tree is too long, then in the last node we have to check all the, I mean, all the roots of subsequent childs. We have to check that is it less or greater than or less than. Only then we can insert.
I think so. For example, you are saying that if you have a binary search tree, already you have a binary search tree, and it
Yes,
contains a long height. Okay,
yes,
so you definitely at the time of, for example, you are inserting a next node, so you will start from the from the root. So, for example, I'm creating one binary search tree. Okay, then tell me where is your confusion. So, for example, 13, 15, 17, 18, and this is 16. Right.
yeah. Now, yes, okay,
Okay.
sir. Now here you have put 30. Then again in the left child there is 10. Then again 5. But in the right child of 5 there is 7. So I know that 7 is greater than 5. But I have to check that is 7 greater than or smaller than 10. Then again if it is smaller, I have to check that is it smaller than 30. it means I have to check all the root nodes.
Yeah, so I think your question is how we can check the tree is a binary search tree or not.
Yes.
Okay, so if you have a tree, if you have a binary search tree, and you are just want to check that is this tree a binary search tree or not. Okay, this is a question.
No, I mean before constructing the tree, we must know that it is smaller than other root nodes, but it is greater than 5. The 7 is
No. So
smaller than.
before actually we construct this tree one by one. We are not construct directly in the one steps. We will insert element one by one. So for example, we have any sequence, so 30, 5, 20, 6, 1, 8, 9, 70, 80, and 15. Okay, we are creating a binary search tree for that. So we will always start from the first node and we will create a binary search tree. Okay, so like 30, this is a root node. And okay, so now we will move to the second node. We will insert this second node in our tree. So 5, we will compare this 30.
Yes.
Okay, and we will check that 5 is lesser than or greater than. Lesser than, so we will move to the left side and check that is there any empty place available or not. So yes, in the left side there is no node. So we will add the same here 5. Now when we move, if we want to move 20, okay, so we will start comparison from the root again. So 20 we will compare.
Now I understood. Okay.
Okay.
I
20
thought
will
we
compare.
will compare. Yeah,
so
I
20
thought
will
we
compare
will
from the
compare,
root.
Yeah, then it's okay.
Okay, now it is 20 is lesser than 30, then we will move to the left side, but node is available on the left. Then we will compare again on the left node. So 20 now is greater than 5. So that means now there is no right child available. That means empty place is available. So we will insert it here. Okay, in that way we are creating a binary search. We are not inserting directly at any place.
Okay.
We are always start from the root node. Then our trees we will create in the correct form.
Okay, sir, again one more doubt I have in week 8 GRPA4. I could not understand the question properly.
This is programming question.
Yes.
Okay.
Yes, 4. Yeah.
This is a MOM algorithm, actually median of medians. I think you have already learned this algorithm in the B content. Okay, so for example, the sequence is given.
Yes.
7 actually. What for simplicity, the size of array will be the multiple of 7. Your solution should be that. So what is the return? The index of first occurrence of M in ERR if it was sorted. So it is this into block of 7 and returns the position of M in ERR sorted. So here one sequence is given.
Yes.
So there is one algorithm taught in the lecture, MOM algorithm, and what is the process of this is. So here one. So here we are asking the median of medians with 7 blocks. Okay. So for 7 blocks, we will select the 7 element first. So first 7 element is this 44, 9, 31, and then this 1, 2, 3, 4, 5, 6, 7. Okay, and 7 block of the 7 element is 1, 2, 3, 4, 6. Okay, so what we will do, we will just sorted the first block. So after sorting the first block, what will be the element is? So this is 9. Just sort this 7th block element 9 and 12, 15, 31, and 44, and 48 and 98. So this is the list after sorting of this first 7th block, and the second block is 6, 13, 23, 35, 45, and then 74. Is there any element left? 23, 35, 74, 75. 75. 1, 2, 3, 4, 5, 6, 7. Okay. Now we got this 2
Yes.
element. Okay. And after that, we will find out the median of the first and the second. This is the median, 2 medians we will get 31 and 45. So
for the second one, it should be 35, I think.
Oh, yes. 35. Yes. So after this, when we are getting this 2 elements, okay, so 0 index we for this and 1 index is actually we are getting this list of this medians. So you can see the algorithms in the B8 where the sir explained this median of medians. This algorithm, okay. So if we are getting the less value of the block 7, so in this algorithm we will take the 7 value, because this is a algorithm median of median with element 5 block of 5 elements. So if we are taking 7, then we will consider the 7 here. So after if the elements in the medians list is lesser than the 7, then we will return this information len of L divided to node value by 2. So len of so that value will return 2 by 2. So 2 by 2, that means 1. So we will return this 35 value. Okay. So that means our median we have selected 35. After that, this is a list, and we will perform the partition operation. Okay, we will select this 35 as a pivot element. Okay, so 35 element have at this position. So what we will do, we will replace this value 35 by first value. So we will replace these things. So we will replace this here 44, and we will replace the 35 here 35. After that, we will apply the simple partition algorithm. So in this partition algorithm, we will select the first element as a pivot, and we will return the so partition algorithm. Basically, what we will do, we will return the actual position of the pivot element in the sorted list. So we will simply, so after sorting, the partition algorithm will return the exact position of this 35. You know the partition. You know the partition algorithm. You have already learned in the quick sort as well as the in B8 quick select.
Yes.
So simply apply this this partition algorithm after finding out this median element. So it will return the answer 7, index 7. So this is the process. Okay.
Okay, sir.
Yeah.
Okay. Thank you.
So
when we talk about quick select algorithm.
Okay, so
So no, I'm not asking the quick select. I know that I have watched your lecture earlier, but the example you have taken that contains values 1, 2, 3, 4, 5, 6, 7, something like consecutive values. But what if we are not taking those consecutive values? Like we are taking some random values. How can we apply them? Because earlier we are just matching whether the index number is basically matching with the value, and we are just returning the indexes based on that value based on the index number.
Okay, so for in the reference of quick select, you are saying that if input list contains the random value.
Yeah.
Okay, so how it can return the fifth the kth smallest element or
Kth smallest element.
Okay, now.
Yeah.
So yeah, same thing. So here this is also a random. You know that?
Yeah.
This is also a random list. We don't know what is the kth. So for example, if we are taking this kth element third, okay, third smallest value. we want to find out. Okay, so same things for quick select, or there is one algorithm also, fast select. In the fast select algorithm, we are using this MOM, but in quick select algorithm, we are simply taking the first element as a pivot. After that, we are performing this task, kth element. So for example, when we are finding out the third smallest element, so we will apply the partition algorithm on this first sequence, and we will select this 44 as a pivot element. Okay, so after partition, this 44 element will come at the actual position. Okay, so for example, this 44 element after completion of the partition algorithm, this 44 element coming in the fifth index. It is clear?
Yeah, okay. it will come to its actual position. That's fine.
Okay, so this 44 will come at the actual position after sorting in the sorted list, and we are getting this information in the after first partition process. We are finding out that this 44 are coming at this fifth index. Okay, that means fifth index means this is the sixth smallest element. We can assume that, because this 44 is coming at that fifth index.
Yeah,
index is started from the 0. That we can say that this is the sixth smallest element.
Yeah.
Okay, and we are searching a third smallest element. So that means after that we will discard the element those are coming after this 44. That means our third smallest element will come before that.
Okay, so we will basically apply the quick select algorithm on the left hand side
on the left part.
Okay,
so we will apply again this quick select algorithm on the left part. Those contain only this 6 element.
So if we talk about the I am not talking about the worst case scenario, but if we talk about the the complexity part, then it should be log n, right?
Not log n, actually partition is taking n time.
Yeah, n log n. Okay.
Not n log n here.
Okay.
Because here we are discarding actually. Here we are discarding completely this part. For example, initially the partition is taking n time. So if you make the recurrence for this, so what will be the recurrence actually? So Tn, initially we are applying this fast select on the n element, and inside it we are dividing a problem into half. So I'm just giving a scenario for the best case or average case. Okay, so we are dividing, that means we are discarding a half of the element and we are applying the same algorithm on the half element. And in the apart from this division process or recursive call process, we are taking n time in the first step. This is a partition time. Okay, so this is a recurrence relation for this quick select. So if you draw the recurrence tree for that, so you can see that we will start from the first node Tn. In the next level, there is only one child. So this is a Tn by 2. Okay, next level Tn by 4. Clear? So
okay, it's go decreasing every time.
Every time it is decreasing. So at this level, total number of operation of the partition is n. And at the next time, number of elements are n by 2. So partition will also take a n by 2.
Yeah.
Okay, here n by 4. That means here this process, this is a decreasing in exponential time. So every time. Okay, so there is one simple formula sir is given in the week 8 when he teaches the recurrence tree. So if the number of operation sequence is decreasing, so in that case we can directly return the complexity Fn. So this is represent actually Fn in recurrence relation. So that means the complexity is n. Okay, but what happened in the worst case? So in worst case, the same process will be applied like as a quick select. So we are performing. So this recurrence relation become like this: Tn and equal to Tn minus 1 and plus n, like this. Because we are thinking in the worst case situation, we are assuming that every time our select pivot element come at the first position, either in the left or either in the right. Okay, so in that case, we have to apply our quick select algorithm on next time and with the n minus 1 element. So in the first phase, our Tn, and the second phase Tn minus 1, and next is Tn minus 2. So number of operation is n here, n minus 1 here, n minus 2 here. So this series will look like
become n square.
Yeah, so 1 plus 2 plus 3, like this. So this is n. So this is becoming n plus 1 divided by 2 because n square. So worst case is become n square. Best and average case is a n. So in the fast select algorithm, we use the MOM algorithm. So basically, MOM algorithm will return the pivot median, closely median algorithm. So in that case, there is no chance to come our pivot element in the one side, the first position or the last position. So because of that, we are improving our worst case situation using this MOM algorithm. So because of that, we are calling this fast select.
So what if we basically won't use the first element as pivot, but we use the middle one as the pivot element? So then the there would be significant improvement in the time complexity of this particular algorithm as well.
You are saying that if we directly pick up the middle element, but we don't want to. So there is other, once again. So maybe middle element always contains a value that come at the first position or last position after the partition process.
Yeah, that might be possible.
Yeah, okay, so this is the random element. No? So if we are taking the first element, so that is a random value. If we are taking a middle element, that is also a random value. So there is no improvement. Worst case thing will remain same.
And sir, if we talk about the overall structure of the quiz 2, so what kind, what I'm not asking what type, like what's the level of this particular quiz?
So level of the person will be similar of the level of quiz 1. You can see that.
Okay, quiz 1.
Okay, so types of the person, basically some property based person can be part of the quiz, or some small code snippet based person also be a part of the quiz. Some calculation numerical based type of.
So will the questions like you will whether you will ask the given the code like full code of particular like 30-40 lines of code and then ask
No.
Okay.
This type of length code is not involved. So if code is given, maximum 10 line, 5 line only.
Okay.
Okay, so this type of actually we know that you have only 45 minutes.
Yeah.
So we are not thinking that.
So mostly like we can expect the property based questions and the
property based and the concept based question, or some small code based questions.
Okay. And there will be like questions on time complexities as well.
Yeah, sure. Yeah. That is a part of your
yeah.
Okay. So this is regarding AVL tree. Yeah, someone is asking for the scheduling things. Okay, I'm taking some questions. I have one peer deck, so I've taken questions from the previous term papers. So I'm sharing this with you, and I'll solve. I think some interval scheduling.
So one more question I just wanted to ask: whether I'm preparing the extra algorithm. So should I prepare it with both the heap and like the code we have coded in week 5, like some general thing. So whether we have to prepare both way or just the concept of Dijkstra should be enough to be present in the.
So for the quiz, actually, I'm not talking about the OPP exam. For the quiz, just learn the concept.
Okay.
Okay, here we are not asking the code directly code for the solution. So we cannot ask this type of code, long code. So, but concept should be clear. If you know that, so if we are getting the higher complexity when we are not using this min heap, and when we are using this min heap, we are improving our complexity. So you can you should remember these things. Using min heap or max heap, we are improving this Traversal algorithm. How we are improving this type of concept you should remember.
Okay.
Okay, so no need to remember the complete code, but for the OPP exam, you should remember the concept of the code. So if you are, for example, in this subject, in this PDSA course, so I think approx 50 to 60 code, I think in the complete syllabus. So how you can learn all the syntax? This is not possible. Okay, so just learn the concept of the algorithm. So for example, you are learning a spanning tree. So just learn the steps, not the syntax. Okay, so simply learn the steps, how you are performing, how you are implementing your code, what step you are performing in the each level. So just remember these steps, and at the time in the exam, just write the code using these steps in memory.
Okay.
Do not try to remember the syntax. So if you are trying to remembering the syntax, definitely you will got error.
Okay, fine.
Okay, so just remember the algorithm steps.
Okay, thank you.
So can you please discuss graded assignment question number, graded assignment 7, question 10?
In which week?
Week 7, question 10. Week 7.
Week 7. So this is week 8. Graded assignment. This one. Question number 10.
Yes, sir.
9. This is 10. So here one tree is given, Huffman tree. I think this is a Huffman tree. So consider the Huffman tree above for encoding. Which of the following are invalid encoding? Okay, so just here some code is given. Okay, and there is one tree is also given. So I think, how can I find the complete tree in one image? Okay. One second.
You can refresh it again.
No, actually, complete image is not coming. So okay, I'm taking this picture.
So will any mock be released?
No. So we are not releasing any mock for quiz 2, but we will release the mock for OPP exam.
Okay.
So this is a tree, and this is the code. I'm also taking the picture of this. Okay. So here one Huffman tree is given, and one code message is given. So simply for validating the code is valid or invalid according to this Huffman tree, simply scan the code and check that code is valid or not. So here always start from the root, and according to this 0 and 1 value, if 0 is coming, then move to the left, and 1 is coming, move to the right. Okay, so for I'm just explaining the first option. You can try after that. So for 0, you will move to the left. Next 0, move to the left, and 1, move to the right, and next 1, move to the right. So at that time, if you are reaching the leaf node, so just mark that at this stage you have reached the C node. That means this code is representing a C. Okay, then reset your pointer on the root node again, and then process again. So same for 0, this time 1. Now you have reached the leaf node. That means next 2 digits are representing a this value D. Okay, you can mark this D. And next for is 1 again, once again, so 1, and next is 0, so that is leaf. Okay, so same things you can mark here. This is a E. And next 1 1, same things, 1 and 1. So this is representing a F 1 1. Okay, so 0 0 next time, 0 0 and 1 1 and 0 here. Okay, so next process is like this. This is a B and it complete here. And next process is 0 0 0. Okay, so this is also complete. So this is a. So in that way you can process your code, and after completion you are getting a valid code here. So valid code means, so there is no bits are left without contain any information. Okay, so here all the bits we have traversed, and after that we have completely get this message. So that means this is a valid.
So if some bits are left and
yes.
there is
no character with reference to that code, so that means that is invalid code. Okay. So for example, if we are traversing this, last time we have reached here and we have get some message till now. Now there is one I think 01 is available, so this is not a correct thing. So for example, we have reached this last 0, only 1 bit is left. Yes. So there is no character for only 1.
Then it is invalid.
That means this is invalid code. Okay.
Okay.
So in that way you can find out this information.
Yes, sir, I got it.
Okay. Yeah, so Sasi, I am just sharing the peer deck. Okay, you can join this peer deck link. I'm okay, pasting the link. Where is the link? Used I have pasted the link of the peer deck. Joined the link, and some person I have taken from the previous term. So I think only 15%. So just try to solve. If you have any doubt, you can ask. Or if you have any other doubt, you can also ask. So join, all of you. I've sent the link in the chat box. Or you can also join this. Open the joinpd.com and enter this code YVVALU. So is there any is the information of students? So are you able to join this peer deck? Can anyone confirm?
Yeah, we can able to.
Yes.
Okay. So yeah, there is one question here I've taken from the previous term. So consider the following binary search tree. The letters indicate the name of the nodes, not the value that are stored. So what is the predecessor node in terms of value of the node M? Okay. So here one tree is given, and we are saying that this is a binary search tree. And what will be the value of the predecessor in terms of the value of M? So what is the way to solve this? Also same things, we you can think about what other type of question we can ask, or in any exam they can ask. So maybe they can ask this type of question also. For example, what is the second smallest element, and what is the third smallest element in this tree? Okay, first return the answer for this question. What is the predecessor of the M in terms of the value? And after that, just also said that what is the second smallest value. So both can be solved using the same way. I'm not getting any response. So are you submitted any response? Oh, okay. I think that. Just typed your answer. So I have not used the MCQ selection option here. Just typed your answer. So all of us, so total is 12 participants. So please all reply on this peer deck. Anything you can reply which you are feeling, what is the answer according to you, you can reply. So when you are practicing on the previous term papers, so at the time of solving each question, so think about the different scenario for that person also. So what other type of question can be possible for those questions? So that will clear your logic also. Okay. So the answer C L G C C G G G L G C. So I'm getting this three value. One is C, G, and L. Okay. Okay. So someone is getting this C, and this is a G, and this is a there is one L. So here we are asking the predecessor node. So predecessor means just one position before this M in terms of the value. So here we are saying that this is a binary search tree. So how we can find out this information in the binary search tree? So simply we can apply the in-order traversal. Okay. So we simply here we can apply the in-order traversal. Okay, we cannot see the value here, so we will directly apply the in-order traversal from on the root node, and in our in-order traversal basically reply the values in increasing order in binary search tree. Okay, so in-order basically contains the information, contains the steps. We will traverse the left node, then print the node, and then move to the traverse the right node. So this is the three steps actually we use the in the in-order traversal. So this is a recursive step, this is also a recursive step, and this is a print statement like this on the current block. So we will apply this in-order traversal step on the each node. So we will get this L. So first step is left. Okay, so we will move to the left, then we will apply this LPR on the B. So now the first step, again this is the left, same things we will apply on the here. So now we will move to the left. Now there is no left, there is so second step is P. Okay, we will get this H value, that means this H will be print, and now we will move to the R step. So there is no R. All three steps are completed. We will move to the back from where we have to come. So second step, so here from D, the first step is L. Now second step is P. Okay, so we will print the D, and third step is move to the right side. So move to the right here, traverse to the right child. Same for here. Now the first step is left, move to the left. Now there is no left. Now the second step will be performed. This is a O. and then we will move to back on the I. So that means we will perform the second step on I. So that this is a print I, and next we will move to the right side. So there is no left. Now the P, and after printing this P, we will move to the I, D, and then we will move to the this B. So this B will be printed here, and move to the right side. So then left side. Now J will print here, and back to the E. So E will print here. Now K. Okay. Now after that, A will be print, and then move to the C, then left, then left. Okay. So L, F, C, then this left. So we can write this M, G, and M, G, and N. So this is a in order traversal for this tree. So here we can return this information. What is the predecessor of M? So you can see that the predecessor of M is C, because in order traversal always print the value in increasing order. So in terms of value, the predecessor of M is C. So this is C is a correct answer. So more question we can also ask, like what is the fourth smallest element in this tree? If we ask this is a binary search tree, what is the fourth smallest element in the tree? So same things after traversing in order traversal. So you can directly return this fourth element. That means fourth smallest element is I. First smallest element is H. Okay, so this type of information you can return using this traversal. Okay, move to the next question. So yeah, this is a same things. We can skip this. Okay, so once code. So lower code is visible to you completely or not? Because I am not able to see this. Yeah, now it is visible. So here one tree is given, some node structure is given, and there is one function is given, traversal. So can you tell me what this code is representing? What type of order it is representing? Can anyone tell me? In the next question number 2. So there is one code is given in the lower side. This is a traversal code. And what type of code is actually? In order, pre-order, and post-order.
The post order.
Okay, post-order. Okay, so can you return the post-order traversal for this tree? So this is a simple code for traversing the tree. In only 3 steps we are performing this traversal algorithms. So if we want to perform in order traversal, just use the print statement before the traverse before the first T left, and to perform for in order, just move to this print statement between a left and right call, and for pre-order just move to this print statement before all left and right. So this is the simple recursive way to traversal the tree. We have received the port response. So post order, actually I am asking that what is the order of the elements? Yeah, this is a post order, correct? Just write the order. Actually we are asking in the question what this function will print. So DHEBIFGCA. Okay. DHEBIFGCA. PHEVIFGC. Okay, so most of the response is this PHEVIFGC. DBHE. This last one is not looking correct. DBHE. Okay. Okay, so for this question, so you can practice on some tree how we can traverse the in order and pre-order and post order in quickly. Okay, so no need to see the code, and so you can directly apply these 3 steps on the diagram and you can quickly print the elements. So simply the step is for the post order traversal is LRP. Okay, so you can apply LRP on the root node. Now first step is left, move to the left, LRP on the left child. Now first step is left, move to the left if node is available, LRP. Now first step is left, no left is available. Now second step, no right is available. Now print. Okay, so first element is print D. So now all 3 steps is complete. Move to the back. Now second step is R. Move to the right. Now first step is LRP. First step is left. Move to the left. Now LRP. So no left, no right. Print H. And move to the back. No right. Now print E. Move to the back. Now print B. And all 3 steps completed. Now move to the back and the right step is available. So move to the right. LRP. So first step is left. LRP. Now first step is left. LRP. First step is left. Okay, so there is no left, no right. Now print I. Okay, now move to the previous. So no right, P, F. And move to the previous. No, yes, right is available. LRP. No left, no right. Print G. And move back. This is C. And move back. Third step is A. So this is the order of post order traversal. So now next, yes, this is the property based question. Which of the following statements is true about complexity of the given function where n is the number of nodes? So same the previous function. Okay, so for the post order traversal, here we are talking about. So for the post order or maybe pre-order and maybe in order, so any of the order, what will be the complex? Which of the following is the correct? So generally, you know that if we have a binary search tree, so what will be the maximum height or what will be the minimum height of the binary search tree? Okay, we will discuss these things for this question. So if we are performing any one of the traversal in order, pre-order and post-order on the tree, on the binary search tree, so which of the following statement is correct?
Sir, it is asking about the complexity of what, like given function, but there is no function.
So I'm already told you, this is talking about the previous question function,
Okay.
traversing algorithm.
Okay.
So any traversing algorithm, either in order, post order, pre-order, this can be asked. Okay. So option C, C and B, C, D, B. Okay. So most of the answer is C, and one is D and one is B. So first option is, so basically here we are traversing the nodes, and every time we are moving each node at least one time. So, okay, so that means n step is actually required. So now here what is the confusion is, if tree is balanced or unbalanced, it's given. Okay, so n step is required. This is confirmed because we are traversing each node. So n step is required. But here the extra information is given whether the tree is balanced or unbalanced. So there is no matter actually if tree may be a balanced or tree may be a unbalanced. So this algorithm will work in the same way. So binary search tree may be a balanced or may be a unbalanced things. So our algorithm will work in the similar way. It will check that if left is available or right is available or not, and according to it will move. So that means
if it is about searching, then it should be log n, right?
About searching, yeah, that in that case, so yeah, I'm talking about this. So this is about the traversing. So here we are actually visiting every single node. So because of that, the complexity is n. So in any way, that if tree is balanced or not balanced, so there's no fact. This things is not affected the complexity of this traversing algorithm because we are traversing each node. So the answer is C. But in the same scenario, what other question can be asked? So for example, sometime ask that what is the worst case of the searching in binary search tree, and what is the best case in searching in the binary search tree. If we are not giving this information, our binary search tree is balanced or unbalanced. So that means it may be a balance or it may be an unbalanced. So in that case, we can think about this: what is the worst case height and best case height of our binary search tree. So worst case height is simply when our node are connected in only in the one side. So for example, we are creating a binary search tree 1, 2, 3, 4, 5 like this sequence. So our tree will be created like this: 1, 2, 3, 4, and 5. Okay. So in that way, our searching algorithm is also will take n time, because our all elements are connected to each other in the linear way like this. So sometimes most of the students are confused, and after listening the name of binary search tree, they directly mark the answer log n.
But sir, this in this case, if I'm talking about AVL tree, so this scenario is not even possible, right?
Yeah, so in AVL tree is a balanced tree now. So
Okay.
AVL tree always generate the balanced tree. In that case, the complexity will be log n.
Okay.
Okay, here we are talking about binary search tree. What is the searching complexity, worst case time for searching in binary search tree? So sometimes student not thinks about this things, the scenario of the binary search tree. If we are not talking about is a balance or not balance. So that things you should remember in your mind. So if we are talking about binary search tree, so binary search tree can be a balance or unbalanced. If the balance term is included in the question with the balanced binary search tree, that means at that time your answer will be log n. Balanced binary search means all the height of the left subtree and the right subtree is approximately equal. So the worst, so if we are talking about the binary search tree, the worst case searching time is n, or we so same question can be asked for the height. So what is the height of the binary search tree in the worst case? That is called the also n. So h called n. Okay, if it contains say n nodes. So same question can be asked in the numerical way. For example, if we have a 10 nodes, so what is the maximum height of that binary search tree? Simply height is also a 10. Okay, and what is the worst? What is the best case height? What is the minimum height? Then we will apply this formula log n. This type. Okay, so in the best case things, so our tree will like this one. So like this node. This is the worst case situation. Okay, like this. If our node is 10, so all nodes will be connected in that way. So this is 7, 8, 9, 10. So you can see if our root node height is 1, 2, 3, 4. So that means 4 height. We will take a floor values for this. So this type of question can be asked. So same for the A.
If we talk about the searching in heap, then it should be n, right?
Yeah, searching in heap is n, because there is no left or right relation in there.
But then it should be n log n, I think.
No, not n log n. You can simply apply the any traversal algorithms. Okay, so
but if we look about its structure, it should be like in general structure, it is stored in a form of some array, like
array or list. Yeah. So you will so if you are searching any element in an array, so what is the complexity is maximum n. So how you are thinking about the log n log n?
No, but like I have to come. Okay, fine. Yeah.
Okay, if it is also given in a tree, so we can simply apply the traversal algorithm. So traversal algorithm complexity is also n. Okay. So same question can be asked for the ABL tree. So I think it will include in this slide. Okay, next question is, so this is also related to some property. This is related to the heights things. Consider a binary search tree of height h. Which of the following statement is true? So yeah, these things I have already discussed, the maximum and minimum things. Six response. So D, D, F, A, D, B, D, B, A, B, B, D. So this time the multiple responses there. B, F, A, D, B, D, B, D, B, D. Okay, now the B, D is the most answer. Okay. So first option is the number of element in the tree is at most h. At most h. Okay, so height is h. So maximum number of it. No. So the first is not correct. Here he is talking about the maximum element can be h. So this is not true. This condition is true for the at least. Yeah. So second option is correct. Okay, if height is given, so that means if height h is given, so h is given, for example, 5. So the maximum and minimum element can be, so minimum element can be when all elements are connected one element. Okay, wait, like this. So this is the minimum element in our node. So the height for this tree is 5, and the element is also 5. This is the minimum situation. And same height, if we create a our complete tree like this, so for height h like this. So this will become a 2 to the power 5 minus 1. Okay, so same things. 2 to the power 5 minus 1. So this is a 31. So maximum number is, so option A is not correct. Option B is correct. The number of elements in the tree is at least 2h. So this is also not correct. So the second option is correct. We can also compare this to C. And D, the number of elements in the tree is at most 2 to the power h minus 1. Yeah, so this is correct. the number of element in the tree is at most 2 to the power x. So this is not correct. Okay, so in a binary search tree, if the number of nodes with 0 child, yeah, so this is also a one property. So in a binary search tree, if the number is equal to n2 plus 1. So this is a correct property. Actually, you can observe these things. So number of leaf node is always one greater than the number of nodes which have 2 childs. So for example, if, so binary search tree. Okay, so for example, I've created 10, 5, 15, 12, 20, like this. So you can see the total number of nodes that contains a 2 child. So this is 1, this is 2, and those nodes contain a 0 child. So that is a 3. Same tree we can create like this. Okay. So here you in this diagram you can see that there is one node that contains 0 child, but there is no node available with 2 child. So that means 0 plus 1, same thing. So you can validate this type of property with some examples. You can return this. So last option is also correct.
But I'm not getting it. Can you explain?
There is one property actually for the binary search tree, or we can say that this property is also true for the no, this is not yeah. So this is also true for the binary search tree. So n0, actually here n0 is representing a number of nodes that contains a 0 child. Okay, n2 represent a number of nodes that contains a 2 childs. So here one relation is given. So n0 value is equal to n2 plus 1. So this condition is always true. Okay, so in binary search tree, you can observe these things. So you can count simply 2 child's nodes. So in this example, so how many number of nodes are available with 0 child? So 1, 2, 3. Okay, so these are the nodes. Those conditions 0. So 3 nodes are, that means n0 equal to 3. And how many nodes are available with 2 childs? So this is a 1 and 2. Okay, so this is n2 equal to 2. So this property is n0 equal to n2 plus 1 is valid for this tree. Same for this. If we count that the number of n0 child node is 1. Okay, this is 1. But there is no nodes available with 2 childs in this type of binary search tree. So that means this is also correct. That means n2 is equal to 0 and n0 equal to n2 plus 1. 0 plus 1 is 1. So you can validate this property. So in binary search tree, always this property is fulfilled. Okay, so you can create any binary search tree, or you can simply validate these things. So okay, so 3 are the correct. B and D and F all are not correct. We move to the next. Yeah, this is scheduling based question. Yeah, so here some activity is given for an activity x s. So suffix s is representing it starting. Okay, activity is started. Is the starting time, and x e is representing a ending time. Suffix e is representing ending time. The following are the starting time and ending time of the activity A, B, C, D, E, F, G, H given in the chronological order. So that means these activities are performing in this order. Okay. So what is the minimum number of rooms required to schedule the activity in a set of rooms? So this is a scheduling way. So how many minimum number of? So you can simply solve this. So there is no response. So the answer is 3333. Okay. 4. Okay. So most of the answer is written as a 3 in chat box. When someone is written the 4. Oh, watching. Okay, I'm sharing the link. 1 second. Okay. So simply we can draw this activity, and so in the quick way how we can find. So here the one AS activity is started. Okay. So we simply write that AS is started. And now the BS, so AS is not completed. Definitely we have to need one separate room. So we will perform this BS. Okay, so here we are just mentioning this is the first room, and this is the second room, and this is not end. So CS, so this is also is separate. So there is no activity completed now. CS, so there, that means third activity is also need one separate room. Okay, after that AE is completed. So AE is completed, that means we have completed one. Now DS, so this is completed. Now we can start DS here, D activity here. Okay, in the first room. So CE, so now CE is end, and I'm just crossing this. CE, now ES, so we can perform E activity here. Okay, so now 3 activities coming on the in 3 rooms. Yes, completed. Now BE, so BE is completed. Now FS, we can perform F from here. So now DE, so now all 3 activities are okay. So this is DE, so this is completed. Now GS, so we can start G here. Now this is EE, so this is completed. HS, so H we can start here. Now FE, this is completed. Now GE, this is completed. Now HE completed. Okay, so maximum 3 rooms are required to perform this. Simply we can draw these things, or we can return the answer 3. So this is simply draw based question. So no starting time and no ending time is given for that question. So other question type, if starting time and ending time is given, so how we can solve. So this is the next one. Oh, this is actually Huffman base. So there is one activity base. Oh, this is here. Okay, now you solve this 10th question. This is also related to scheduling question. And then we will come back to the previous. So meeting M1, M2, M11 are to be conducted in a single meet available room. And the table is given here with the start and end time. If any activity finish at time t, then other activity can be started at time t or afterward. So what is the maximum number of activity we can perform without any confliction? So conflict means no activity can be performed in the time overlapping time. Okay, so we can see that. So any activity can be stopped at the time of the completion time t or afterwards of the other activity. Oh, there is no option. Okay, I think. So someone is asking in the initial how we can solve this scheduling based question. So this is a interval scheduling related questions. So to solve this, we should perform some steps. So first step is sort your activity according to the end time in increasing order. Okay, so first step is sort the activity in increasing order of their end time. And then start selection from first question.
There is no space provided for the answer.
Oh, because of that, I'm not getting any answer. Okay, so just paste your answer in the chat box for this question. I think I not connected the option. Five. Okay. Yeah, so others can also reply your answer in chat box for this question only. Okay, so you can change the answer. Okay, till now I am performing the first step to solve. So what is the order? What should be the order after sorting? So we can see the what is the minimum end time is 3. Okay, so M2 we will take 2. This is the start time. This is the end time. 3. Now the next minimum value is 5. So this is for M8 and 3, 5. Next value is 7. Okay, so this is M1, 4, 7. Next one is this is 7. So M10 is 2, 7. So this is 8, 8, sorry, 7, 6, 8, 9. So M6, 6, 7, 9, then M9, 6, 9. Now next is 11. So M5 is 10, 11. Then so M3 and M4. Okay, I'm writing here. So M3, 11, 12, M4, 9, 12. And then M11, 13, 15. Okay, so this is increasing order. Okay, I'm seeing the answers. So now the most of the answer is 6. Okay. So now we can, after sorting the activity according to the end time in increasing order, so we can start the selection from the first activity. So we will select this, okay, and we will compare the next activity starting time from the last activity ending time. If both are equal, then we can select that also. If the starting time is greater than the end time from the previous, we can select. But if the starting time is the less than from the compared to the previous activity end time, so then we will not select. Okay, so for the first activity we will select, and so here you can see that these both value are equal. That means we can also select this one. Now here the starting for the M1 activity, you can see that the starting time 4 is lesser than this 5. So that means we cannot select this. Same for the M10. So now starting time is 2 and the ending time of M8 is 5. So we cannot select this. Now M7, you can select this because here the starting time is 6 and last activity end time is 5. This is greater than. So we can select. Now the end time is this. We will compare with this. Now next activity is started at 7, but last activity ending time is 8. So we will not select this. Now next same things. This is 6 and last is 8. This is smaller than, we cannot select this. Now next activity is F5, which is greater than starting time. So we can select. Now the ending time is, so we will compare this 11. So now you can see that we can select M3 also because time is equal. So now the end time is 12 to compare. Now the next activity we can select M4 because no, we cannot select because this is 9 and this is 12. But we can select M11 because the time is greater than. So you can see that how many activity we are selecting here. So total number of 1, 2, 3, 4, 5, 6. So total 6. 6 activity we can select in one row. Yeah, so this selection order can be different. So here we cannot return the exact answer. Maybe someone can apply the different types of algorithm. So maybe he can also return the. So for last example, so maybe it's not last. So yeah. Okay, so for example, this 7, this order can be different. Okay, and the sorting same for the this. In this this order can be different, this order can also be different. So we cannot return the exact answer what activity we are selecting, but the number of activity will remain the same. Okay, so that can be validated. So correct answer is 6 for this. Now moving to the back. So I think we are here. Okay. So this is related to the Huffman codes. Here some probability is given. So can you tell me what the number of bits required for this? A, B, C, D, E. So Huffman based many question can be many type of question can be asked on the basis of the Huffman concept. On the property base also.
So we have to find the average bit length.
No. So how many bits will be used to encode the message? Here message is given A, B, C, D, E. So just find out the length of the A bits. Okay. Just add all these. Okay, so for this question, I've received only 4 response, and answer is 1, 13, 12, 13. Okay. So here we can draw the Huffman tree using this value. So you know that how we can create a Huffman tree. We start from the minimum to smallest frequency. So what is the smallest frequency of minimum span? So this is 0.16 and this is 0.11. So we will create from the bottom side. So for example, we can write in any way. So for example, this is 0.21 and this is 0.11. Okay, then we can create this 0.21 and 0.11 is 0.33. Okay, so now we have selected all these. So now we have new weights is new frequencies 22, 33, and 21, and this 30. Okay, so what is the next two smallest value is this 22. Sorry, I have written wrong. 16. Okay, so this will become 27. Okay, so now next smallest two smallest is 22 and 21. So we will create a separate 0.22 and 0.21. So it become a 43.43. So now we have selected this. Now the combination of this 0.43 and now combination of this is 0.27. Now we have 3. So these two are smallest 0.30 and 27. So we can create a 0.30 here. Now we will create node. This is representing 57. Right. Now after that we will add both. So it become a 1, 0, 0. Okay, so this 0.16 is represent C, 0.11 is represent E, and 0.222 is represent A, 0.21 is represent B, and 0.30 represent D. Now you can find out the length of each port. So we can directly write, for example, A. So what is the length of the A? So I'm not okay. I can return the code also. 0, 0. For each left node, we will assign the 0, and for each right node, we will assign the 1 value. Okay. After that, what is the code of A is 1, 0. What is the B is 1, 1. C is 1, 0, 1, 0. What is D is 0, 0. What is the code length of E is 0, 1, 1. Okay, so simply you can add 2 length of each code to 3, 2, and 3. So this is simply 6, 3, 9 or the 12. This is the answer for this question. So 12, yeah, 12 is the correct answer.
I have one small query in this.
Mm-hmm.
Number of total digits is okay, 12. Suppose if it is asked what is the code for C, it is coming as 0, 1, 0 now. When we are starting, we are putting C on left and E on right. Okay, it is a random choice. If we are putting 0.11 on left and 0.16 on right, no, then the code for C will be 0, 1, 1. Correct, no?
Yes.
So such things how to avoid. If it is code wise asked, what is the code for C kind of thing question is coming.
Yeah, so code wise thing, I think one question is given or in your assignments.
Yes. So,
okay, so here
since
some
it is a random, here itself, no, if we are putting C and D in a swap way, it can be 0, 1, 1.
Yeah, yeah.
So
I'm getting a point. So you can say that there are multiple codes can be generated.
Yes, but when it is asked, no, how we will come to know that it is correct code, whether 0, 1, 1 is the correct code or 0, 1, 0 is the
so where actually some multiple things can be possible, so that type of question cannot be asked. Otherwise, some condition they will definitely will give it. So how you will add the left child, how will select the
finding
right.
the trick will be
So same thing in the previous question. So there is a multiple activity can be possible for the selection.
Yes. And the same way, if you are putting the entire A, B, 3 no on the left hand side, all the things will be changed. 0, 0 will be changed to 1. 0, 0 and 1.
But code length, so what code length will not be changed.
Code length will not be changed. That's correct. But
yeah,
if it has to be decodification problem, then it will be an issue.
Yes, yes.
Okay.
So multiple codes can be generated if condition is not given for the left child or right child, because we can take in any way. So for example, 2 value is the similar or for C and E, so we can take in any direction, so either in left or right. So multiple codes can be generated. So but there is one property. So in property ways, so some person can be asked. So for example, if we have a 5 character A, B, C, D, and A, B, C, D, E, like this. Okay, we have 5 characters and code is given. So for example, some random Huffman code is given. So for A is given 0, 1, B is given like this 1, 1, C is given 1, 0, 1. Okay, D is given like that. So 0, 1, 1, and E is given 1, 0, 1, 1, like this. Okay. So can you tell me this is a valid code or invalid code?
Invalid code. D is having prefix of A.
Yeah.
0, 1, 1, 0, 1.
So this type of question can also be asked because here we can verify this code is valid or not using this prefix property. Okay, so Huffman code is always generate the prefix code. So that means any code of any character cannot be a prefix of other codes.
Yes.
So here you can see that this information you can find out the 0, 1 is coming in this code initially.
Yes, yes.
So that is a prefix code. This should not be. So the same things for 1, 0, 1.
One more 1, 0, 1, 1, 0, 1.
Yeah. So this is also a prefix. So you can validate your Huffman codes using this property, prefix property.
Yeah. Okay.
Sir, can you please explain how Huffman coding work? I mean the encoding and the 0, 1 part. So Harshjit, what is your exact query regarding this?
Sir, how you did 0 1 in the edges, and how you encoding the 1 0 0 1?
Yeah, so after creating a Huffman tree, so you know the how we can how we are creating a
Yes,
Huffman tree.
yes. This part is clear.
Okay, this part is clear.
Mm.
So after that, we just assign a 0 value on the left edge, left child edge, and 1 value on the right side edge. So this process we are performing. On every left edge, we are assigning a 0 value, or every right edge, we are assigning a 1 value. 1 second.
Okay, and after that, how you did 1 A 1 0 B 1 1?
Yeah. So for calculating the codes, we always start from the root. So this actually this value a value is representing this 0.22 value is representing a. Okay. So for calculate the code for this a, we will traverse from the root, and we will just appending the value on each edge. So for traversing from the root, we will traverse like this. Okay, from the
Yes,
root
sir.
node we will traverse like this. We will traverse on the right, then we will traverse on the left. So we will reach at the a node. So what numbers are coming on the edge? So we will append in this equals to 1.
Okay.
This 0.
We have
This
to
is for
consider
A.
from the parent root, from the root to the leaf,
Yeah,
right?
so you just traverse the path from the root node to that leaf node. Just use the value on each edge in this path. So this is representing a Huffman code. Okay.
Yeah, got it. Yeah.
So next question is this. So this is the binary search space. I think it is easy. You can all solve this, but sometimes many of the candidates mark the wrong answer for that also. Here we have a one sequence, and just tell me what is the element at maximum depth. Just create a binary search tree for that. Okay. So 30 and 65. Okay. So 3 response have received. Just create a binary search tree using this sequence and check that what elements are coming at the highest depth. So, okay, so in the response, 30, 60, we have 30, 60, we have 35, 60, 90, and 10. Okay. So 35 and 60 and 90 and 10. So maybe you are not creating a correct binary search tree. So okay, I'll tell you what is the way to create a binary search tree again. This is sequence. Okay, so here's one sequence is given. Just create a binary search tree. So one answer is sorry, I typed wrong. Okay. Okay, Sasiya. Yeah, so here how we can create a binary search tree. So I have already tell this process in the initial of the session. So we will start from the first node and consider this is in root. And after that, according to the property of binary search tree, we will always we will start from the comparison from the root node, and at any time when we found the empty place, we will insert. So 80 is greater than 50. Now place is available, so we will insert 80. Now 20 is smaller than the root, then space is also available on the left. So 20. Now 60 is greater than 50, but we will compare to the right child. Now this is a 60 is a lesser than 80, so we will add this in left of the. This is 60. Now 10, so 10 is lesser than 50. Now we will move to the left. Now node is available. We will compare again. So 10 is less than this 20. We'll move to the left. No node is available. Then we will insert this 10. Now 45 is lesser than 50, greater than 20. Then space is available here. We will insert this here. Okay. Now 65 greater than 50, lesser than 80. Greater than this 60, this means it come here 65. 30 lesser than 50, greater than 20, lesser than 45, 30 will come here. And this 90, so 90 will greater than 50, greater than 80. So you can see this 30 and 65 are coming at the lower depth, maximum depth. This is the answer. Okay. Yeah, so these are some property of the AVL tree. If you remember this property, this is also important. Sometimes so the numerical question can be asked using this property. So which of the following is true about AVL? Assume that the height of the empty tree is 0. Okay, so AB, BCD, ABC, BCDE, ACD. I know that most of you, maybe you have solved this type of questions, so you are quickly reply on that and you are not reading the property properly. So 3 options I have get this A, and A. Yeah, out of 5, so 3 have marked A is the correct answer. But I think this is not a correct answer. So if you see the property of A correctly, so some formula change is here actually. LSH denote the minimum number of nodes in an AVL tree of height h. Then SH equal to SH minus 1 plus HS minus 2 minus 1 is given here. So read the statement properly completely, after that select answer. So maybe that is looking similar, so you are selecting quickly. So but here minus 1 is given in the actual formula. This is a plus 1. So because of that, this is not a correct answer, A option. Okay, in AVL tree, the absolute difference between the height of the left subtree and the height of the right subtree of any code can't be more than 1. So yeah, this is the correct property. This is basically for the balance factor for each node. The left height minus right height absolute value should be less than 1. Sorry, less than 2. Okay, so now options 3. The complexity of searching in an AVL tree is order of log n. So this is correct. Yeah, that means B, C is correct. Now, if the height of the AVL tree is S, the maximum number of nodes will be 2 to the power h minus 1. This is also correct, because this is a situation for the complete binary tree with the full levels. So this is B, C, D is correct. The complexity of both insertion and deletion in AVL tree is big order of n. So this is not correct, because we can insert insertion and deletion in AVL tree is a operation of log n operation. Okay, so
could you please explain A?
So A is property actually basically sh equal to sh minus 1 plus sh minus 2. This should be a plus 1, not the minus 1. So if you can see that what are the minimum number of nodes of the height. So for example, if we have a 0, so s0 equal to 0 nodes. Okay, s1 is represented like this in that way. So if we have only one nodes, so this is a possibility. If we have a height 1, that means minimum number of node is 1. Sorry, 1. Okay, s2 situation, what is the minimum number of node is we will just simply add these two value and add plus 1. So this is a situation like this. So if we add like this, so this is also a AVL tree, and this is not a unbalanced. Okay, so here left part is contains the height 1, and there is no right part. This contains height 0. So total height we will consider left height plus right height plus 1. Okay, so not left height. So we will add the previous things. That means this component is combining by these previous two AVL tree, and we are adding one node before that. So this is the possibility. So here we can simply add the s0 plus s1 plus 1. This is representing it 2. Same for s3. Now you can see that now we have a one node for s1, and this is not the correct. Okay, so this is for 1, this is for 2. Okay, so we will add these below. So this is a one newly node added we have, and we will add this part on the left and this part on the right, or maybe this part on the right and this part on the left, this type of things. So we can add like this. So okay, this slide and these things. Okay, so this is representing a s2. This is representing a s1, and here we are adding a one new nodes plus 1. So because of that, we are just adding this previous value s1 plus s2 plus 1. So the total number of nodes is so this is 1, this is 2, and this is plus 1, 4. Okay, so this is the minimum number of nodes in the AVL tree. That means this tree should also be a balance, and that is the minimum possibility. So here the correct formula is sh equal to sh minus 1 plus sh minus 2 plus 1. This is the correct formula for the minimum number of nodes. Okay, so BCD is the answer, correct answer for that. Okay, let's move to the next. Okay, I have already discussed this, so I'm ignoring this part. Which one is the valid code? So here we can check using this prefix things. We can validate these codes using this prefix information. So we have already solved. Yeah, now the next question is question number 11. So Bimlis, these questions are also available in. So these all questions I have taken from the previous term papers. So I think that the links of the previous papers is available on the discourse openly, so you can see that all these questions from there. These are the not new questions. So 105. So we will share this joint on our drive. Okay, so if you have joined this PDX session, I think you can look this question after this session also. If you did for quiz 1 revision session. Oh, I forgot that what I did in the quiz 1. So in quiz 2, approx 15 or 16% is there, not more than. So same pattern we are following, 15 or 16, maximum 16.
Sir, again, same question. Like if we are able to solve these questions, we'll able to solve the quiz questions.
If you are able to solve these questions.
Yeah.
So yes, so question, I'm not saying that the exact question will be asked in the quiz. So maybe some different question.
Like
so,
concept wise, like.
Yeah, so I've taken this question from the previous term actual papers. Okay, so you can think this thing. So these are the actual questions which have already come in the previous term quiz.
Okay.
Okay, so if you are able easily this type of questions, so definitely you can solve the quiz paper also. That means your concept is clear.
Fine.
So maybe some new person you will see. So that things I cannot disclose. Okay, so the answer for this 105, 105, 105, yes, 4, this 4 and 1, yeah. So the formula is also given 15 into 15 minus 2. So this 105 is the correct answer. There is one direct formula is given in the lectures. You can
minus 1 by 2.
Yeah, n into n minus 1 by 2. You can directly apply on that. So 15 into 15 by 2, you can directly calculate using 105. Okay, so next question is also related to this. Okay, so same things for the inversion numbers. So if you have if you have a list this L, so the number of inversion for this list with the same property of inversion. Yeah, so most of the answer are 5 or 1 is 2. Okay. So I think sir explained one method using the diagram. Okay, and you can simply calculate it. So for this is a smaller list, you can simply calculate the inversion numbers. So here we can directly calculate like this: 1, 4, 3, 6, 2, 5. This is the one process, and then now we will written in the sorted order: 1, 2, 3, 4, 5, 6. Just match the each number by the line. So you can see 1, 2, 4, 3. Okay, so 6 and 5, and this is okay. Now all are connect.
Problem is, if we scale it and do it manually also, then there could be a concurrent point. I'm just, if someone is in a hurry, geometrically it could be concurrent point.
Okay. 1, 2, 3, 4, 5. So 5 is the correct answer. If you are getting this answer in that way, so maybe concurrent point means
Means this triangle between the lines 4, 4, 3, 3 and 2, 2, they could go from the one single point if we draw it to.
Okay, yeah. So in some way they can get the incorrect answer.
I'm so
Otherwise,
sorry. I'm so sorry. It won't be possible because 2 is far away in the upper line.
yeah, but maybe someone can draw the point on the same line mistakenly if they are mistakenly draw the incorrect line. So you can simply process like this. So you can start from the first position and just check that what are the elements which are not in the incorrect order comparison. So okay, for first, that is this is the smallest value. Okay, so all the value after that is coming, those are, all are the greater. So that means for one there is no inversion. Now for check for the 4. Okay, so how many value are coming after that, this 4 which are smaller than this one? Okay, so you can find this 4 3 and 4 1 combination. Okay, so this is for 4. Now check for the 3.
No, 4 3 and 4 2. No.
Oh yeah, 4 2.
Yeah, got it. This method we understand.
Okay, so for 3 same things. Now 3 2 is the in incorrect order according to the sorting. Now for the 6 we will check 6 2 and 6 5. After that for 2 there is no, and 5 there is no. So that means these are the 5 inversions. Okay, fine. Yeah, so what is the complexity?
The last question, if there are some numbers repeating, how do we approach that? Like the method you explained, dot methods.
Number is repeating.
Yeah, suppose 6 is repeated twice. How do we approach?
So I think
it shouldn't repeat. Why? Because it is a preference. I mean, someone's preference.
So
candidate A's preference given by same movie is being given different preference by candidate B within the same range. So it is like number of different items.
All are distinct. Okay.
Yes.
Yeah, all should be distinct. Yeah.
Okay.
Yeah. So for the next question, this is one. Yeah. What is the complexity for the following recurrence? So this is related to the last topics of the BK. That is also a more important topics for the finding the complexity of for the recurrence solution, recursive solution. We can say
N square.
N square. Okay, think about it again.
It's already been discussed.
Yeah, I've already discussed in the previous, I think, week 8 session.
No, you have explained me this thing actually right away.
In the previous, I think yeah, I have discussed these things.
Log. Log.
Yeah, for quick sort, quick select. So okay, we will discuss again. For binary search, this n value will become a 1. Okay, so this is a quick select recurrence. We can see that so binary search, if we remove this n by 1, so that become a recurrence for binary search.
Log n.
So if you see the property in the last lecture, so there are actually sir explained these 3 property. You can remember this property and just like this. So this is the conclusion of this topic. So this is the decreasing way. This is the decreasing. If the total number of operations are decreasing, you can directly write the complexity Tn equal to order of Fn. If the number of operations at each level are the remains same, so we can directly write the complexity log n. If the number of operations at each level are increasing exponentially, so we can calculate the complexity using this formula. Okay, so these 3 important points you can learn. So using this, we can find the complexity. So for the first column, so what is the first? Okay. So Tn Tn by 2 plus n. Okay, so this is the recurrence equal to Tn by 2 plus 1. Sorry, n. So we are starting. So this is a recurrence relation. So at every time we are calling the same recursive function on n by 2. So we are starting from the n element input, and in the processing of this process, we are just applying the same algorithm recursively on n by 2 elements, and apart from that, total number of operation we are performing n operation. If our input is n, total number of operation is n. So this is called the Fn. So you can draw the recurrence tree. So this is the Tn initially. Now at the second level, we are just calling on the 1/2 part. So n by half part. So we can see that Tn by 2. And the next level it will become more half. So Tn by 4. Okay. So total number of operation required at the first level is n. The second level will become a n by 2, and third level become n by 4. So this sequence is a decreasing. Okay, so this is the first condition. So here we can directly write the complexity f. So complexity is order of Fn. So this Fn is this. So this is becoming n. Okay. So this is the first, and all three questions are approximately similar. So now this is the what is the complexity for the following recurrence? Here Tn equal to 2t n by 2 plus n.
Log.
Tn equal to 2t n by 2 plus n. Okay, so we can draw the recurrence tree. So Tn initially, now we are calling 2 times n by 2 and T n by 2. Okay, same for the next level, T n by 4, T n by 4, and this is T n by 4, and this is also T n by 4. Okay, now you can calculate the number of operation apart from this recursive call. This is total n operation. Here, this is a Tn. So here total number of operation is n by 2. This is also n by 2. If we add both, we will get n. So same for n by 4, n by 4, n by 4,
n by 2, n by 2 we are doing.
So at this level, this problem is taking a n by 2 operation. If we are applying individually both. Okay, so here we are. This is taking n by 2 of number of operations. This is taking n by 2. So the total number of operations at this level is
so
n.
at each level it is n only.
Yeah. So here same things, n by 4 plus n by 4 plus n by 4 plus n by 4. It is also becoming n. Okay. In that case, you can directly, if the number of operations are equal, so you can simply write the complexity
log n.
Not log n, Fn into log n.
Okay, yeah, n log n.
N log.
N log n.
Yeah, if you see the property, so this is a equal case. Okay, so here Fn into log n. So this is a property. So here this is n, and you can combine this n log. And this is the last one. So here the value is increasing. So Tn 4t n by 2 plus n. So Tn equal to 4t n by 2 plus n. Okay, so if you draw the tree for this is, so it become like this. So Tn
2 and it will be.
Okay, so Tn by 2, Tn by 2, Tn by 2, Tn by 2. It's the same for every child. So at this level, total number of operations n, but here we are adding n by 2 plus n by 2 plus n by 2 plus n by 2, it becomes 2n. Okay, so same for the next level, total 16 level is 16 into n by 4, so 16 into n by 4 become 4n. So actually this is increasing, so we can write simply this is 2 to the power 0, this is 2 to the power 1, this is 2 to the power 2. So this is actually exponentially it is increasing. So in this case we will just compare this formula. Sorry. Yeah, this. So Tn equal to order of n log Cr. Okay, so this is the formula. Tn equal to order of n log Cr. Now what is C and R? C is basically a division value. C is basically a division value where what division we are using for the dividing the element. This is C equal to 2, and this is a R value, R equal to 4. So we'll directly apply this. So n to the power. Okay, sorry. This is n to the power. So n to the power log 2 is 2 to the power square. So this will become a 2. So it's becoming n square. Order of n square. Okay. So this is the way to calculate the complexity of the recurrence relation. So now the question we have completed. If you have any query in any other topics, now you can ask. Okay. Okay, so any query in any topics?
Sir, could you please explain graded assignment 8, question 4 and 5?
Graded assignment week which
week 8.
Week 8. Graded assignment 4 and 5.
Graded assignment, yes.
Okay, this one. So here first question is the basic of the recurrence relation. Okay. So which of the following option describe the recurrence relation that will give the above recurrence tree if the cost of the combining solution at each level is equal to 2n? So here one cost is given, and you can see the division part here. So every time we are dividing a problem into two parts, okay, the one part contain the input n by 3 and second part contain the input 2n by 3. So we can directly write these things: Tn equal to Tn plus n by 3 plus T2n by 3. This is the first thing. Now what are the numbers? So in the last option, so in the Fn part, we can write the exact number of operation as well as we can write the complexity for that part. So both are the correct things in the recurrence relation. So in the first option, the total number of operation is given, and for the corresponding this number of operation, what will be the complexity we can take? We can take order of n. Okay, so in the recurrence relation, we can represent both things. We can represent Fn equal to a complexity also. We can represent Fn equal to a number of operation also. So both are the correct things. But here actually when we are writing a number of operations, so we cannot change the number of operation. So here this is a 2n. So here we are writing a n. So this is incorrect. And the third option is incorrect because we are not dividing it correctly.
I have one small query. So this, if you add all level 2, it is coming n only. All level 3 also n only. Every levels it is add, if you add n only. So should we be second option or first option? This is the problem.
So you are talking about the question number 5?
No. The same question. Yeah.
Same for
how the 2n is selected correctly instead of n.
So this 2n is given in the problem statement. So if the cost to combine solution at each level is equal to 2n.
Oh.
This is given in the problem statement.
We added this it was coming n, all the things, so I put the n.
No. So number of operation given in that recurrence relation, not in the tree. Tree is not represent the number of operation at each level. This information is given in the recurrence relation. Okay. So
from the recurrence relation, if we are forming the tree, we are just basis t equal to tn by 2. We are not taking the number of operations to combine.
Yeah, so here there is no information
subsequent step.
Yes, so here in the recurrence tree we only represent the how input size is dividing at each level. So apart from this dividing process, how many number of operation we are extra required, so this information is not given at the recurrence tree. This information is given in the recurrence relation. So the next question number 5 is if order of Fn is the upper bound of for the above recurrence series, what is the value of Fn? So now you can think that so total number of operation at each level is. So if we are performing this number of operation, so if we can find out this 2n, basically we are just converting this to the order of n. Okay, so the actually this number of operation will remain same,
which is 2n.
Yeah, which is 2n. At each level this number of operation will remain same.
So it is a constant kind of thing.
So constant type of things, but the number of level actually will be log 2 to the power here the maximum depth will be 2 to the power here, so this is the maximum size. So n by which value is the greater, n by 9 or 2n by 9?
2n by 9.
2n by 9. So this actually this right part will be moved so till one value. So I think this right part will move deeper, highest depth. So because of that, so we can directly calculate the formula if the value at each level, number of operation at each level is constant. Okay, so this is n, this is n, this is n. So we can directly write the complexity Fn into log n. Okay, so Fn is equal to n. So we just add the log n. So total complexity will become n log n.
But in the question, it's asking Fn is the upper bound. So
yeah, so upper bound. This is upper bound, no? Actually.
Yeah, but Fn is order of n, right?
Yeah, order of big O with the big O. So generally we calculate the complexity with big O.
If it is saying of or big O of Fn is the upper bound.
Yeah, this here this big O is representing a upper bound.
Fn part, right?
Sorry.
We will consider only the Fn part, right? If n log n is the total complexity of it, that.
So Fn actually Fn part is n, but so total number of levels are required here. So that is the log n.
The question is same as the time complexity of the 9th question, right? Fourth question.
Yeah, both questions are similar on the same point for the same tree.
So it's so confusing. It's saying Fn is the upper bound. So we are considering only the 2n part.
No. So total number of operation is 2n. Actually, for complexity, we will take order of n here. Okay. So Fn, if you are taking 2n and according to this formula. So if you can simply okay, just 1 second.
Yeah, I got that point, the complexity of the question, the TN part. Okay. But I'm confused with the question.
Okay, so upper bound, actually when we are using upper bound thing, so that means we are asking the complexity with big O. So most of the time we calculate the complexity with big O. Here normally the best case things, actually best case can be anything. So for example, if our problem size is 2, okay, yeah, so in that case the complexity will become 1.
I thought we need to consider only the FN part. No need to consider whole TN part.
No, I'm not getting what actually you are saying. So here, if you are seeing this tree, okay.
I got this part, the complexity of this part, but the question is so confusing.
Okay.
James is just asking the value of FN. See, in the question it is given if big of FN is okay. So it's just asking the value of Fn, that should be n log n. If you place the value in that particular equation, that it will be big of n log n. Okay, so that is the question is asking the value of Fn.
So yeah, so here this is given that if big O Fn is the upper bound for the above recurrence relation, what is the value of Fn? So this Fn is representing the total Fn value for the complete
function.
Yeah, complete function. Yeah.
Okay.
Okay. So because of that, this is converting into n log n.
Could you please explain 5 again, question 5 again?
So question 5 is basically if you draw the tree, so you can see that what are the recurrence relation for this is. So Tn equal to Tn by 3 plus T2n by 3 plus 2n. Okay, this is a recurrence relation. So you can see that at this level, this number of operation is 2n. So if you add these things here also, so this is also 2n by 3 plus 4n by 3. So this will also become a 2n. Same things at this level also, you will get this 2n. So at each level, total number of operation we are getting 2n that are fixed. Okay, so in that case, if number of operations are not increasing, not decreasing, and that are equal at each level, so we can directly take this complexity Fn log n, Fn into log n. So here Fn equal to 2n, or for 2n log n, we can ignore this constant. So this become a order of n log n directly. Okay.
In the explanation, it was given log 3 by 2n.
Yeah, so actually here we ignore these things. If we are getting the log based different value, so here the differentiation is not dividing half every time. So because of this type of division, 2 by 9. So this is the division actually. So n by 3. So this is 2 by 3. So if we take this value lower, so this become a n by 3 by 2. Okay, this become a n by 3. Actually, this is a smaller value. This is a greater value. Okay, so that means the height of the tree will be based on this greater value. So because of that, if we are taking this as a base. So when we divide the value by 2 every time, so n into n by 2, n by 2. So at that time, this 2 become a base of the log 2n for this height. But if our input is decreasing in that way, so if you see this n, after that n divided by 3 by 2, then again we will divide this by this factor. So our log formula will become changed. So this become a 3 by 2.
So if at each stage we are dividing not equally, but in some ratio, then the smaller denominator becomes the base of the log. Like
Smaller,
here,
yeah,
3 is
yes,
bigger
yes,
than
yes,
3 by 2. So 3 by
yes,
2 is
yes,
a smaller denominator. So
yes,
that will become the base of the log.
yes, yes. But we actually, this is approx equivalent to this log 2.
That
So
is
because of
okay.
that, we
But then
convert.
this log 3 by 2, what is the logic in choosing a smaller denominator?
Because if you divide the, for example, one side, this is a n. Okay, one side you are dividing n by 2. Okay, n by 2. For example, you have a 8 value, and you are dividing one side, you are dividing by 2, and one side you are dividing by smaller value, so not 2. So for example, here you are dividing by 4, and here you are dividing by 2. So n by 4, and here you are dividing by n by 2. So what the, so our height will goes more down this side. So for example, this will come
Let
a
us
4.
n by 4, n by 4, n by 2. Let us do that.
So for this value, for example, this 8 by 4 is become 2. Okay, and the next level, this become a 2 by 4. So it will become, so at this time we will reach earlier. So when we are dividing by the bigger divisor, so we will reach earlier at the value 1 compared to the second part. So we will
Okay,
consider
so
the
okay, so got it. So overall height of the tree
yeah,
will be decided by the lower one.
yes,
Because it will take, okay, got it.
Okay.
Sir, I have a question regarding minimum cost spanning tree.
Minimum spanning tree, okay. Which person?
Yeah, I will read the question. This is last year question.
Okay.
Let G be the complete undirected graph on 4 vertices,
Okay,
having 6 edges.
Okay, got it. I'm writing that. The information is given. We have 4 vertices, and the edge weights are given
6.
1, 2, 3, 4, 5, and 6.
Yeah.
Okay.
That's the,
so what are the maximum possible weight for the minimum spanning tree?
Yeah.
Okay. So here you can see that we can draw the 4 nodes. So A, B, C, D. Okay. Now we can create a by spanning tree using these weights. So for example, we are applying the Kruskal algorithms. So Kruskal algorithm will always select the minimum base first. So we will select this way. So this can be on any, so this one weight can be connect on any 2 vertex. For example, it is connecting this. Okay. So there is no problem with this. Now we will select the second edge 2. So we can also connect this 2 at any place in the spanning tree. So this edge can be also a part of at any place. So for example, if we are taking this as a 2, so here there is no problem because 2 edge cannot be created a cycle. Okay, so 2 edge cannot be created a cycle in our spanning tree. But when we are choosing this 3, so we can think about this. Can we ignore this? Can we this edge skip? So how this edge can be skipped? If it is coming, it is creating a cycle. For example, if this is creating a cycle, so for example, this is coming at this place 3. So for spanning tree, we cannot choose this.
But it can be CD also.
Yeah, it can be CD also, but our question is, what is the maximum possibility? If you are taking CD, so if you are taking CD, so your minimum spanning tree will complete at this stage. So say if you are adding this CD with 3, so now this now our minimum spanning tree have completed. Now we cannot take any edge after that. Okay, so now the weight is 1 plus 2 plus 3 is 6. But in our question, it is asking that what is the maximum possible. So maximum possible, we can take this scenario So for example, if this 3 is creating a cycle, so this is a possibility. So if this 3 is creating a cycle in our original graph, so we will not select it. Okay, in that case we will not select it, and then we will move to the next edge, 4. So this 4 can be either can be connect either AD, BD or CD. So after selecting this 4 bit, our tree will become minimum spanning tree. Okay, so 4. So that means we can make this scenario. So we can skip this 3. Now in this scenario, now we are getting this 1, 2, 4. 1 plus 2 plus 4.
7.
To 7. So this is the maximum possibility of the weight. This is also a minimum spanning tree.
If the question is minimum, they can return 6, right?
Yeah, if question is asking that what is the minimum cost of the minimum spanning tree,
okay,
so that will be 6.
Okay, thanks.
Okay, here we are asking the maximum.
Okay.
Any other query?
Sir, graded assignment 6, question 6. I mean, there are 2, 3, 4, 5, 4, 5 questions. How to? Yes, week 6.
Okay. Which question?
Question 6 or 4 or 5, whichever. I mean, one has
to. 4 question is simply you have to find out that what is the type of this heap.
Yeah. So how to approach this problem? I mean, one has to create.
Just create a complete vanity. Just create a complete vanity of the sequence. Okay. After that, just check the property of each parent and their childs. So for example, the sequence is given 88, 77. So this is a simple sequence I'm writing here. So 88, 77, 66, 55, 44, 33, 22, and 1. So actually this is representing a heap. So we can directly draw the complete vanity. So 88, now the next cell is 77, now 66, this is 44, this is, 55, 44, this is 33, this is 22, this is 11. Okay, now you can see that the property, what property it is actually storing. So here you can see every parent is greater than their child. So this parent is greater than their child. Now this parent is also greater than their child. This parent is also greater than their child. And this parent is also greater than their child. So you can return this is a maxi. All parents are.
So, in question 6, I mean, one has to try creating maps or both type of heaps. Then only one can understand its none.
Yeah. So for this 4, 1, 2. Okay. So 4, 1, 2. And next sequence is 3, 5, 6, 7, 8. 3, 5, 6, 7, 8. Okay, just create a tree. 4, 1, 2, 3, 5, 6, 7, 8. Okay, just check is this tree is following the maximum max heap property. So for max heap property, just check that child value is the lesser than the parent's value. So this is okay. Now here you can see that this parent value is greater than, but here this is the parent value. Sorry, here the parent value is smaller than their child's. On now upper side, the parent value is lesser, greater than their child's. So that
so basically one has to assume that the question given will be for a heap structure only, and accordingly one has to draw the tree and identify whether it is actually a heap structure or not.
Yes, it is following any property of max heap or min heap. If it is not following any property of the max heap, min heap, that means this is not a heap.
So mechanically we will fill from try to create a tree from left to right in the array.
Yes, it's complete vanity.
Okay,
this is called the complete
there's no
vanity.
There's no need to make it a heap like structure.
Make heap? Sorry.
I mean, we could make a. I mean, the question is not asking to create a heap structured out of the
Yes, yes.
given
Yeah.
element.
So here we are not asking to create. Here we are just asking. This is a one basically a list. So, okay. This is basically an array. So this is a actually max heap, min heap, or this is a normal array.
Yeah, so that's like top to bottom, left to right. One has to fill
Yes,
in the
yes.
array elements and then decide.
So generally, actually, we always create a max heap, min heap using the array, not the tree structure.
Yes.
Okay, so this parent-child things we can create using the index. So
Yeah, in other question can be formed like given this array, create a max heap or min heap, and
yeah. So
what
that
should
type
be
of
the
also given. So this is a array. Just create a max heap or min heap. So at that time we will apply the build heap algorithms on the complete array.
Sure.
So I think you know the process of the building of max heap or building of
yes. I mean, create nodes, fill the nodes, and then heapify.
Yeah, just heapify process. Any other question in this?
No, that's all.
Okay.
I mean, could you please explain question 1 also in this, the theory part?
Yeah, this one. Consider a list with k distinct element numbers and a heap h with size n. What is the nearest upper bound for checking if every number in L is present in the heap h? Okay. Focus the list with k distinct number and a heap h size. What is the nearest upper bound? So every number in L is present in the heap. So actually we are searching element here. Okay. So you know that in the searching operation in heap takes n time.
For each element.
For each element. For each single element, the searching operation takes n times. Here the total number of elements k. So that takes the k n time. Okay. Others, if you have any query? Okay. So, I think we should close this session.
In this question 7, why not option B? What is wrong with option B?
Option B. So what is the question? So which of the following will correctly represent the max heap after inserting element 1 to this? So just creating a heap and just check that what elements are coming in the list. Okay. So this sequence is given. So you can create a max heap. So we will insert one by one element here. So we will insert one. So we can see that this is a max heap. Okay. After inserting two, so two element will be insert at this position. Okay. So after that we will make a max heap. So after making max heap, it become a like this 2, 1. After heapifying process. Now we will add 3. So in this, so we will add 3. Now we will apply the heapify process on that. So it will become a 3, 1, and 2. Okay, fine. Now we will add 5. So our 5 element will be add here. Okay. Now so element can be moved on the path from last inserted position to the parent root node. Okay, so we will compare this element from the parent node. If this is not in the order, we will swap, and then we will again compare with the parent node. So in the insert things, we can follow this rule. So now will our max heap will become like this. So this will become 5, and this will become 3. This will become 1, 2. Now at the time of insertion 7, so 7 will come here. So 7 will move in that way. So our structure will like this: 7, 5, 3, and 1, 2. So now this is a maxi till now. Now 6th element will come here, 6. So now it will move here. So 7, 5, 6, 2, and this is 1, and this is 3. Okay. And after that, 4 is only remaining. So 4 we will insert directly because it is lesser, so it will not, no need to swap. After that, just write the element.
Could you please scroll up a little?
Which one?
Could you please scroll up? Yeah, just a second.
Okay.
2, 1, 3. I committed a mistake here. I mean, it's 2 and 3. I didn't swap 2 and 3. Okay, sir. Got it.
Okay. So the sequence is coming finally.
These things take time.
Yeah. So quickly calculation, it takes time. So actually, after practicing, so definitely you can quickly solve these things. Okay.
And what other kind of theoretical questions could be asked, sir? Just to understand.
So theoretical question basically based on the concept. So like so what is the syllabus week 5 to week 8? So what is the concept of minimum spanning tree? These things, properties of the digest algorithm, Bellman algorithms. What are the difference between these things? These are so property based on the algorithms. That can be asked. Some numerical type of question like this. Okay, min max or heap. Like, so if we are inserting these 2 elements in the last, so what will be the structure of the heap? So this type of numerical question can be created. So question will be similar to this graded assignment of the previous term question paper. So most of the question will be based on the conceptual. Okay.
So like that, this question was there in graded assignment 7 out of ABCDE encoding and 1000 characters long message. That question was there.
Which one? Graded assignment 7. I think number of bits we are asking. It is related to the Huffman codes.
Yes, question 9.
Mm-hmm. So this is also related to the. So here is the question. Yeah, this one now. Okay. So this is actually probability is given. Okay,
Yeah,
the table of probability of each
this
character is given.
entire thing is okay. Only thing is calculation intensive.
So this is not much typical calculation. Just create a Huffman tree. After that, finding out the bit length of each character. Okay, just multiply this 22 value by the length of the each character, and again just divide. So this is representing 100 character. Okay.
Yes, the options, if options are far apart, then it's less prone to commit mistake. But here options are close enough, and while doing addition, someone may commit a mistake.
So I think a calculator is available on the portal. So if you are not using the calculator, so that is your mistake. You are using the calculator, so I think it should be correct. I think calculator is available on the TCS portal also.
Yes, it is available. I mean, I haven't checked in quiz 1. There was no requirement, but earlier it was available.
Okay, okay. Actually, I did not see the interface of the TCS. Okay.
Yeah, thank you for the session, sir. If anything, we'll post.
Yeah, sure. You can post on the discourse.
Yeah. Thank you, sir.
Okay. Thank you, everyone. If you have any query later, so you can ask on the discourse. Just post on the discourse. We will reply as soon as possible. Okay. Thank you all, and all the best for your quiz too.
Thank you, sir.
Someone is asking, would week 5 to 8 carry more weightage? Actually, most of the question will come from the week 5 to 8. Actually, we just say these things. Syllabus is 1 to 8 because some topics are interrelated to the previous weeks, like complexity. You have learned the complexity in week 2, but the complexity based question can be asked in the week 5 to 8 also. So mainly syllabus is from week 5 to 8. Okay, thank you all.